Hello guys, Sir DV is back again here to solve a particular problem on beam column. So the problem's actually a brace column from which the forces were drawn from the analysis, and the values of the forces, the loads and the moments are actually in terms of the total service loads, and it is actually indicated in the problem that we consider those values as contributed by the dead and the live loads equally. So 50% of which is coming from the dead loads and 50% are coming from the live loads. So the load combination is therefore given here in terms of so this is the contribution of the dead load, and this is the contribution of the live load. So it's true with the moments, or 50% of the moments are due to dead load and 50% are due to live load. So we will be guided accordingly by this load combination, where P and M are the results of the loads shown here. So this is 250 and 240. So the moments are equal at both ends. Of course, the actual load is also equal to satisfy equilibrium conditions. So the column members are W12 by 106 with a length of 14 feet, and the effective length factor K for both the considerations on the end the restraints are equal to 0. So we are using A992 steel grade 50 with Fy is equal to 50 KSI, and we are asked to answer these questions 1 to 15. So these questions are actually chronologically arranged to give you the step-by-step procedure on how to come up with a solution on the determination of the adequacy of a beam column. So this is actually a simple beam column procedure. Okay, so this except for number 15, wherein we're just asked to find the value of k in addition to the assumed value of k equals to 1.0, maybe for the purpose of comparison. Okay, we later summarize the answers, and this is an instruction to the quiz takers just for compliance. So I have here now the property of a W6 or W12 by 106, which is indicated here. The bending, rather, before I forget, the bending direction is actually about the strong axis, which means that these moments here are actually resisted by the strong axis of bending. So if you take a section here, your wide flange is actually oriented in this manner, wherein the bending is about the x-axis. Okay, so this is the property of W106. And for the first part, we of course define the given parameters we need in order to solve for the unknowns. We have the P, the M. So the units are in kips and foot kips. No? So they are consistently placed in kip foot, and for the stresses, we have here the KSIs. Okay. Of course, this is in inch square. So these are in inch and inch. So for the factored forces, we refer to the equation 1 and 2 and just plug in the value of P 250 and M equals 240. We get these values here in terms of kips and in terms of foot kips or kip foot. So for the local flange buckling check in compression, we simply have to again get this value from the table. So automatically the value is 6.17 and 15.9 for the width to thickness ratio of the element. No? So this is 6.17 and 15.9 compared to the limits. Okay, so this is the limits provided by the AISC. So it's 0.56 square root of E over Fy and 1.49 square root of E over Fy. So we are referring here limits for uniform compressions because there are also some limitations on local buckling wherein the reference is on flexural compression. So as we take a look into the comparison, this is less than the limits, therefore we don't have any problem at all for the local flange buckling and the local web buckling. So the answer for the two questions here is simply no. Okay, so will there be any local buckling on the flange and on the web? So the answer here is there is no flange buckling. Okay, there's no web buckling. So for the lateral torsional buckling, so we come up with a formula. This is an old formula, but you can use the newer formula, which is rather more, shall I say, critical, and this is more conservative. Therefore, we get a value of 10.985 as your limit. Okay, so this is the limit for your um, lateral brace to ensure a plastic, okay, behavior as far as the moment capacity is concerned. So this is the limit, which is 10.985, and we have the brace length to be at end to end of the beam, so which is 14 feet. So therefore, this exceeds the limit, then your beam is laterally unsupported. So we can actually continue solving this by simply taking note of the interpolative formula, wherein your uh, value of mn, okay, is actually on this linear. Okay, so this is now your lb and this is your mn, which is in between your lp and your lr. So if you want to take the value of mn here, we simply make use of a Ratian proportion or simply a linear interpolation of this. Okay, but this is MP, and of course right here is your MR. But we don't need to do that because we are asked to find a remedy on question number 5. What would you recommend if there's a lateral torsional buckling? So the answer here is to simply add a lateral brace, maybe somewhere at the mid-span or exactly at the midpoint to satisfy the lateral torsional buckling requirement, meaning to say that your beam will be divided into lengths which is not greater than 10.985. So if you put a midpoint bracing, then at 7 feet, your LB now becomes 7 foot or 7 feet, which is still less than 10.985, which is the limit. Okay, so for the actual load capacity, we now make use of the LRFT formula. FCR is equal to 0.658 raised to, this is a lambda c squared value, which is Fy over Fe times Fy. But first we need to compare the actual slenderness ratio. Okay, so this is now the slenderness ratio, KL over R, okay, with that of the limit of your slenderness ratio, which is given in the code as 4.71 squared of E over Fy 113.432. So in ASD, this is actually your C sub C in ASD. Okay. So again, the slenderness ratio is not exceeding the limit. Therefore, if we look into our graph of curve, okay, column strength curve. So this is your inelastic buckling, and this is your elastic buckling. So your limit is actually at 113.43, and your point into which your KL over R slenderness is only at this point, which is 54.02. Okay, so basically your value of FCR lies on this point, which is equivalent to the formula we have in LRFT. Okay, so we can use also the formula of ASD, but in this case, try to use the formula of FCR in terms of this formula in LRFT. And upon solving your FCR, which is in KSI, so we simply multiply this by your reduction factor PC, which is 0.9, and AG multiplied by AG to come up with a forced value equivalent to 1,134 kips. Okay, so for number 7, we take the moment gradient coefficient. So we have two formula for the moment gradient coefficient. The first one is actually your parabolic formula, and this is the 1993 nonlinear formula. Okay, so if we look into the moment, if this is your beam column, the moment is actually equal-ended. Okay, so this is equal, M1 and M2 are equal. So wherever you cut, okay, you put a brace here, still your M1, M2 will still be the same, such that your M1 is simply equal to MU, which we have computed, and M2 is equal to the negative of MU. So this is for the sense of bending. For single curvature bending, your M1 over M2 is always negative. So that if I divide M1 and M2 here, I simply get a negative value. So this will be subtracted. So this is simply 0.7, and this is squared. So this is positive 0.3. So this becomes 1.0. For your 1993 formula, we'll be using the values of Mmax, Ma, Mb, and Mc, which are of course the quarter and midpoint values here. Okay, so this is now the quarter point value, which is still the same as M1 and M2. So this is just equal to Mu, and Ma, therefore, Mb and Mc and Mmax are just the same. And if we add up to this, so this will now be equivalent to, I think there's an error here. This must be 3. Okay, so this is 12.5. 3 plus 3 plus 4 plus 2.5 is 12.5. So automatically this is 1.0. So there's an error on the formula. We do a recomputation on this. This is exactly 1.0. So whatever formula you use, you will yield to the same value. For the shape factor, all we have to do is to divide the plastic modulus with the section modulus on the basis of direction of the bending. No? So for shape factor x, you get cx over sx, and for shape factor y, you get zy all over sy. And we can readily get this from the table, and upon uh, getting the ratio, we come up with a 1.131 and 1.523. But of course, we are interested with simply the x bending direction, which is this one, because our frame of a reference on the bending is the x-axis. For the plastic moment, we now simply make use of the formula MP is equal to CXFY, but this is in kip inch because your Fy is in KSI, so I simply divide it by 12 to get a value there of kip foot. For the moment capacity, so we have here your bending moment reduction factor 0.9, again your BF over 2TF and H over TW are given here from the table again, okay? And comparing it with the limits of which are flange limit, local backling for bending is 0.38 square root of E over Fy, and the web limit for flexural backling, or sorry, local flange backling for flexure is 3.76 square root of E over Fy. So these are all coming from the ACI width to thickness ratio limits. Okay, so if we are going to compare your flange 6.17, again this is less than, and this is also less than. Therefore, our conclusion is that the section is compact. So we don't have any problem now on compactness requirement and lateral torsional backling because we have remedied it a while ago. So our bracing requirement is therefore satisfied due to that. So we can take now the moment capacity phi bmn simply equivalent to phi b times mn1, where mn1 is simply the plastic moment, which is in terms of the unit kip foot. Okay, so I divided by 12 to maintain the unit in kip foot. So my moment capacity now is simply 615 kip foot or foot kips. So for the modification factor Cm, we have your M1 is equal to Mu and M2 is equal to Mu. Take note that here we have a change of sign due to single curvature. Okay, so it's positive, and a double curvature it's negative. So these are from the AISC sense of the bending moment based on curvatures. Okay, so we have now M1 and M2 are in single curvature. They're both positive, so this becomes 1. And if you take a look at the formula, this will simply yield to a value Cm equals 1.0. So for the magnification factor, we have the strong axis of bending, which is the x-axis. We first get your Px, which is simply the Euler buckling load. Given by the formula pi squared E over KL over R squared. So we are on x-axis, so this must be Rx. The 12 there is simply to convert your length into inch so that this will be consistent. Okay, so this is in KSI, this is in inch this is in inch and this is in inch, so this will cancel out. Your PEX now will simply be in KSI multiplied by inch squared for the area, gives you now a value of kips. And this will be used in getting your alpha or alpha x in the direction of x bending, which is equivalent to P over PEX, so this is 0.037 upon using the AISC formula for B1 for brace. Okay, so this is for brace columns or brace frames. We get now the value of 1.038. And to get the interaction equation without magnification, we simply use or ignore first your B1 here to get your value equivalent to 0.794, and here we put the value of B1 and check whether it will still be safe, and our conclusion is that this is actually less than 1, and therefore this is adequate both for unmagnified and magnified moments. Before I forget, okay, so you use this formula. uh, uh, First, you have to base it on the ratio of P over phi CPN, and this must be greater than 0.20. In case this is less than 0.20, then it is some modification of the factor of safety here is uh, changed. Okay, so we have to come up with another formula when your P over PCPN is less than 0.20. But in this case, if you are going to check PU, which is equivalent to the value of 350, and VCPN equivalent to a value of 1134. Okay, so 350 over 1134 will yield 1134 will yield to a value greater than 0.20. For the slenderness factor K, is no longer included on the complete procedure. So this is an additional question to solve for the slenderness factor K using the British equation. If psi 1 is assumed to be 1.0 and psi 2 is assumed to be 0.50, so these are now the two equations we can refer to, and taking note that if you get two values here, we simply choose the smaller value to get a more economical, okay, parameter in the design analysis procedure. So that ends the complete solution on how to deal with the beam columns considering brace frames. I hope you have learned this simple procedure uh, in the analysis of steel columns using the AISC moment magnification method. Thank you very much for listening. Have a nice day. See you on the next video.